if you look at the data center capacity growth over the past couple of years, they have been growing tremendously. The US grid simply does not have enough power to support this much growth. So I'm going to try to give you a little different perspective than the previous talks in my talk. So with the theme of the conference, Democratizing Intelligence, I thought about what this means to me and then how it relates to my research. To me, it means enabling efficient models so that everyone can access to it, not just the ones that they can afford, but it also means moving beyond efficiency and enabling sustainability so that we don't deplete the resources of the earth while enabling this technology. So you all know this probably, but writing one email with GPT-4 costs a bottle of water and 14 LEDs light up for 1 hour. This is just one email using 100 words. So how do we make these systems efficient and sustainable? But first, what do I mean by efficiency and sustainability from the first place? By making the models efficient, don't we make them sustainable as well? So does anyone here knows about the Jevons paradox? So Jevons was a British economist who lived in the Industrial Revolution era. And he observed the car manufacturing process. And what we found that as the car manufacturing becomes more efficient, as the cars become more fuel efficient, people actually drove more. And overall fuel usage increased rather than decreasing. So this means efficiency is not necessarily equal to sustainability. If we apply the same car analogy to AI, as we make the models more efficient, more people will try to deploy for more use cases, and the overall usage will increase. In fact, if you look at the data center capacity growth over the past couple of years, they have been growing tremendously. The US grid simply does not have enough power to support this much growth. And all the AI companies across the board are investing in large nuclear energy projects to support the data center capacity growth. So, and in the meanwhile, if you look at the trends of compute infrastructure versus the revenue, the costs are far exceeding the revenue coming from the LLMs. When the demand is high and then the resources are low, I'm going to argue that the sustainability is important because when the resources of the earth are finite, manufacturing is finite, power generation is finite, only the ones that they can afford will be able to develop AI technology. Therefore, I think it's crucial to make the AI infrastructure sustainable. But how do we make it sustainable? So if you look at AI's life cycle carbon footprint, it includes two components: operational carbon footprint and embodied carbon footprint. Operational footprint coming from the emissions associated with the energy consumption while running your model. And things like optimizing for renewable energy and time of the day and location of the data centers, these become very important. On the embodied carbon side, that is coming from the manufacturing of the hardware. And you can make carbon optimal hardware choices and optimize for the lifetime of the hardware. To enable these type of optimizations at FAIR, we developed an architectural carbon modeling tool called ACT, available on GitHub, to be able to make such hardware design choices. But in my research, I also look into optimizing the total carbon footprint holistically as well. And I want to talk about a recent project we developed in the space called CatTransformers. So CatTransformers is a model and architecture search framework that takes carbon footprint into account during the design stage. So we take a pre-trained transformer model, prune it across different dimensions such as number of layers, FFN dimensions, attention heads, and we make it fit to an optimal hardware architecture using design parameters like number of cores, core dimensions, memory capacity, and size. So by doing such a joint model and hardware architecture search, we show that we can reduce the carbon footprint of the models significantly. And some of the key takeaways from the CatTransformers project was the optimizing for total carbon footprint yielded different model and hardware architecture parameters than optimizing for traditional metrics like energy or latency. So if you only optimize for latency, your latency will be low, but your total carbon footprint will be high. If you optimize for energy consumption, it seems to strike a balance between latency and carbon footprint. But if you optimize for total carbon footprint, you can actually achieve lowest carbon footprint at the cost of slightly increased latency, but still within under your latency target budget. This shows the importance of optimizing carbon footprint as a metric in your design. If you'd like to read more about scaling AI sustainably, all of the work that I mentioned and the tools are open sourced, and you can find it under Facebook research/sustainable AI. I want to highlight two of the papers that we recently published, Sustainable AI and Beyond Efficiency. You can find all of the links at the repository. Thank you.
So in terms of like changes of the architecture that you saw when you were optimizing for carbon, what was the dominant change in the architecture that allowed significantly better carbon emissions?
The main difference comes from like the ratio of operational and embodied carbon. When you're designing the area much bigger, when you're making the area bigger, you lower the latency. That reduces the operational carbon, but then the embodied carbon increases. So there's like a trade-off between reducing latency, reduces operational carbon, but increases embodied carbon, if that makes sense. So while optimizing for total carbon, you are trying to balance the increase coming from latency with the area of the chip, if that makes sense.
Yeah, I was curious about the hardware optimization part of the search space. Like, what level of granularity are you talking about? Like, you're not designing custom chips, are you? Is it like what?
Yeah, this is more for like edge accelerator use cases that we are targeting. And we use a simulator to basically design different hardware architecture parameters.
Got it. Thanks.
Have you, in your research, started to consider energy consumption at the systems level? So right now you've been talking about chip design. Obviously, when there's a transition from electrical interconnect to optical, things like silicon photonics or micro LED, there should be some benefits in terms of energy efficiency. Or is that an area that you plan on sort of exploring in the future?
That would be an interesting area for future research. We haven't looked at it yet. Thank you.